Hey everyone, I'm Mikey, and I'm going to talk about nature's best practices for distributed systems. So, yeah, that's me. That's my avatar. I come from this group called Inspiral. We're a network of companies that are trying to do business a little bit differently. You can kind of think of us like a little bit of reformed hippies who want to do business. So the slides are up once we get back to the normal internet. They're up there on the website, and yeah. This is my first time being in Camp.js. It's been pretty sweet, and it's good to be here. And I might say things that are a little bit weird. I'll use some imprecise terminology. Yeah, just go with it. So, overview. First, talking about like what systems are, just generally. Then talking about sort of the popular practices that people use when doing systems and why they might not be a good idea. Then I'll talk about natural systems, what sorts of traits and commonalities that are found in natural systems. And then I'll talk about a new approach to distributed systems that are more based on local subjectiveness. And then using Patchwork as an example. So, systems, what are they? So I'm going to say systems are defined by the networks, who you connect to. So they're sort of the topology, who you're allowed to say things to. There's the messages, there's what you say to them. So it could be any sort of message or packet of information. For natural things, it's like the chemicals or the sounds or whatever. And then there's signaling, there's how you connect, there's like what's the dance you're going to play, and sort of the protocols of interaction. And so examples of this would be like ecological systems, like we have here. It's doing this nice little system-y thing with lots of rain, wind, it's pretty sweet. Or socioeconomic systems, like how we interact business to business, or people, consumers and producers and all that. Or political systems, like how we make decisions, how we run governments, how we do things. So, I found it useful to think about systems as a coordination problem. Most systems are really just about getting people or getting some things to interact together in order to do something. And what that thing is might vary, but it's really, systems are about coordinating. And so, but when you're coordinating, there's a common problem where everyone agrees that there's something that you should do, and yet not everyone's doing it. So the example is like climate change. Any intelligent person would agree that we should be doing something about it, but we're not, or at least we're not doing it enough. So whether it's there's bad actors or we're waiting for someone to start doing something, we're just, there's not enough happening. And maybe we should look to systems of how we could, maybe that means our system isn't working as well as it should, and maybe we need to do some refactoring, maybe some just large-scale rewriting. So why nature? To be honest, nature is better at distributed systems than we are. It's really hard to kill life. Like if you want to kill the fungus spores in your fridge, good luck, they're just going to keep coming back. And in this, there's no question that the planet will survive climate change. It will change and things will happen, but it's going to still be there. The question is whether we will still be there. So with it, something that nature does differently, in normal systems and coordination, we do central planning. So we have central governments, we have central committees, we have sort of top-down hierarchical approaches. And it's our kind of go-to system of how we deal with coordination, because it kind of works. Like if we want to say, we need to have this, everyone needs to be obeying these regulations, there's something to that. But there's also an interesting thing where nature doesn't do that. Nature sort of doesn't have top-down control. It just has all these independent agents that somehow are coordinating, and they're coordinating without central control, and they're coordinating under severe constraints. So they don't have lots of energy, they might not have much communication range, they might have limited language, but they're still able to do this coordination quite effectively. And I mean, it's not like nature's perfect, nature does its own things, but there's some things I think we can learn from. And so, now getting to popular distributed networks, what sorts of things are out there in the wild. So we have the internet decentralized, also kind of not, but looking at some parts of it, so the internet's pretty fragile. I'm just going to take, for example, the Border Gateway Protocol. This is how people can sort of assert ownership over IP addresses. They can say, okay, I'm in control of these IP addresses, these link to me. And there's been some problems over the years where people have basically either maliciously or just by being incompetent, they've misconfigured things, so they've asserted that they owned IP addresses. There's a common case in where China, whether it's just misconfiguration or whatever, said, okay, we own the IP addresses for YouTube, and then there was all this packets going transferred kind of in the wrong direction. And normally that'd be fine. Like, I think trust is a good way to build up networks, but we're sort of, because there's so few participants on the internet, there's so few ISPs, then we're really putting all of our eggs in one basket. Like, we have one internet. If it ever goes down, and in this case, like, the misconfiguration propagated within less than a minute, so they just rapid change, and any mistake means that the whole internet is gone. So it's not that it's, it's just, we're really keeping things a little too close, and if something goes wrong, it goes really wrong. And there's even a Twitter feed of BPG, or BGP hijacks, which I find quite interesting. And so you can see, like, and if you are doing stuff like that, it is very good to know, IP addresses. Another example would be name registries. Common pattern is having this global namespace. And so DNS is a global namespace of our domain names, and so it's, I'm dinosaur.is, and it's useful in having this global namespace, possibly. There's like Namecoin, which is more distributed, where we distribute the registration process. We make it so there's not just the ICANN or whoever's in charge of registration, but we now have this protocol where we're going to have global consensus on who does registration, but we're not distributing the registry itself, so we still are fascinated with the idea of a global registry, and I'm just not convinced that it's necessarily a good idea. You don't really see global registries in nature. It's not like this is the thing and there can be no other ones like this. Things are much more subjective in nature. And I think a good example would be like how we deal with nicknames in real life. Like, people can call each other whatever they want. They don't say, oh, well, I already have a friend named Bob, so I'm sorry, you can't be Bob. But if it was like that for the whole world, like, I can do that and be like, okay, well, now I know two Bobs, so you're going to be like Bob H and Bob L. But it's not going to be like we need to consent across the whole world about who each name is. And then we get weird things with like Twitter handles and stuff, such as one handle. So the next example, mobile phone networks. Here, we're known as service. We have phones that have radios. They can communicate over wirelessly, but we can't because the base station is down. So we have this thing where it's kind of peer-to-peer-ish, and I think this is, I'm bringing up as like a common pattern. So it's this pattern where we have a peer, and then a middleman, and then a peer. There is the sharing economy stuff, or also known as like the renting economy, where you have Uber and Airbnb, where they're acting as the middleman between peers. So we're not trading directly, we're trading through this middleman. And then it just means the peers are at the mercy of the middleman. So whether it's the base station goes down or Uber wants to rack up prices, we don't have control because we're just completely at the mercy of the middleman. An example is just buying a bicycle with a neighbor. So if I want to buy a bicycle, normally I could just like, even if I don't know my neighbor, but we live in the same city or something. So with Bitcoin, I have to send a message to some complete strangers. I've never met them. They could be living who knows where. Those are called the miners. And I'm going to participate in some global consensus process. So in order to exchange with my neighbor, I need to now know where all the coins are in the world, and I need to create this consensus process about, basically participate in this global ledger with people I've never met. I have no idea who they are. I have no sort of relation to them, but yet now we're just doing this global consensus process. Meanwhile, I'm, probably only within a few degrees of trust with my neighbor. Like if we live in the same city, hopefully we probably have some mutual friends or mutual friends. So we could just be doing a little bit more of local consensus, and we don't need to just try to get everyone in the world participating in the same system in order to do anything. And the cost of that is that, in the case of Bitcoin, because we're doing this global consensus process, we create this lottery. The lottery is called proof of work. And then we're doing, every 10 minutes of just CPU cycles, or now in ASIC cycles, to basically just do hashing, which is a completely meaningless process. Like, we already know that hash functions are as they are. We don't really need to be computing them over and over again, and just basically wasting resources. So next example, more just, in this case, Twitter is not necessarily decentralized, but it is a good example of how we're building social systems. On Twitter, everyone's connected to everyone, and because everyone's connected to everyone, then it's really easy to abuse someone on Twitter. You can basically just mention someone and be like, blah, 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 blah. And the problem with that is it's an opt-in open, so it's by default, anyone can send you a message. It's the same as like email. By default, anyone can email you. And so it's really the victim, the one who's getting attacked, who has to expend energy to defend himself, rather than the person who's offending has to like get permission to talk with that person. And yeah, this sort of just comes up in a bunch of different places. So other example, downloading a file with BitTorrent. When I download a file with BitTorrent, it's another system where it's just everyone connects to everyone. I'm going to connect to some random strangers to get it. In this case, maybe it's useful. We're going to connect to exchange files, and maybe not enough people in the world have this file. But the process of me just connecting to random people means that it's easy to monitor who's downloading what. So someone could just sit in the network and say, okay, who's trying to connect to me and who's trying to get what? And there's no way to sort of share within a local network. So you're just sort of picking and choosing from anyone who has a file and just getting it from them. So in general, the more social perspective of this is we're converging on a monoculture. We're converging on, we all sort of are acting in very similar ways, we're doing very similar things, we're thinking in very similar ways. And the problem of that is more that we're disagreeing in the same ways. We'll have discussions and we sort of talk about fostering like, we want diverse opinions, diverse ways of thinking, but usually it's only the same disagreements, and we don't have enough people who are really coming at it from completely different angles. And I think that's what we're missing, that's what nature has. Nature has species that have never interacted in the lifespan of the world, and I think that is actually useful. And so I think it's good to keep in mind like what narratives and metaphors we use to express ourselves, and how much is like bias or blind what we're thinking. Because diversity is good. We have like, in this process of convergence, we're now basically eliminating languages, we're eliminating species, and we're just putting all our eggs in one basket. And so it could be good, but if things go bad, it's going to be real bad. So now looking at natural systems. Natural systems are quite simple. So commonly we build systems that are quite complex. So you think of like the OAuth dance. We've all implemented where you just like, you got to have this one, and you have that one, and you have to do another order. And so it can be quite complex, and you have to like do things synchronously and in order. Most natural systems are asynchronous, and we just have kind of a spray of messages. They're not necessarily in order, or they're just kind of like traversing out. They could be unary messages, which is just like a beat, where it's the same type of message every time. Usually there's like little to no stored memory. So it's just kind of, things can be very forgetful, but still work out. And often there's like what's called the one-to-many principle. So in, let's say, proteins traveling through a cell membrane, it will keep track of like how the concentration of proteins, and it will know, okay, has it passed the threshold or hasn't? It doesn't need to know exactly how many there are. It just needs to know, okay, it's either above or below this threshold. So things can be quite, it doesn't actually need to know all the information. And maybe we don't need things that are actually contain all the complexity we think we need. Another common trait of natural systems is that they're randomized over deterministic. So by randomized it means they're like stochastic. They're unpredictable, that are due to random variables, and so in our systems they'll be what we call like deterministic. So we run them again, they'll run in the same way, and we have this whole idea of the Turing machine and computation. We usually refer to things with unique identifiers, which I think is quite useful. I've actually, like, in this thing, I still think, yeah, computation, determinism, like cryptography. But now I'm trying to think, okay, like what would a random system look like where all the nodes are anonymous, they're all based on randomness. If you think of your brain actually is not deterministic, it's probabilistic. And so if you think about things, if you were to like isolate your brain and sort of give it the same inputs, it will actually have different outputs because it's just going to probabilistically have the right thoughts. So I found that quite interesting. And there's the small world topology, where a lot of these systems that I brought up before, they're based on the everyone's connected to everyone topology. And usually nature, or pretty much nature doesn't often have that. Nature instead has the small world topology, and the small world topology is where everyone's not connected to everyone. You're only connected to a few people, but you're only a few hops away from everyone. So you could think of like the human networks are like this. We have the 6 degrees of Kevin Bacon, so everyone's within 6 degrees of Kevin Bacon. There's Wikipedia's like this. There's a game of like, you start somewhere and you try to get somewhere and you figure out how many hops it takes to get there. And the reason for this is that you want to, in nature it comes up because you want to isolate where the attacks are coming from, or you want to isolate where the noise is coming from. So you want to keep things separate and using topology as a mechanism, as opposed to cryptography. So with this, instead of using sophisticated consensus algorithms or cryptography or any of this, nature just uses the topology to handle errors. So the first one we have is like the densely connected networks. There's the ones that are, you're not worried about noise, you're less worried about attacks, so they'll be very fast. And that's why I think a lot of digital networks are built this way, because it's very fast to do things like this. But they're robust to a single point attack. Like if one node is being targeted, then that'll be fine. Like it's only one node. But if one node's being targeted and can start affecting other nodes, then you're in for a real problem, because everyone's connected to everyone. Next, you have like the weakly connected, so kind of like the modules. It's still fast because you're within the modules, but it's not robust to single point attacks because you can just like attack the hub. And you see viruses that are programmed to attack like specific DNA in our system that are like the hub proteins, the proteins that are involved in all sorts of cell replication. And they're doing that because they know that they'll sort of get into every system. But in this case, we are protected by cascading failure because it could block up one module, but then it won't spread to their modules. And something we have often in natural networks is the idea of like the sparsely connected, where things will be much slower because there's more hops to get somewhere, but it also means it's resilient against the single point attacks and the cascading attacks. So another common thing in nature is the idea of like the fractal scaling. You sort of have things composed at the layers. So we have the human organism, where I'm composed of organs, and then in the organs are tissues, and the tissues are cells, and cells are organelles, and kind of just keeps going down and down and down, the smaller bits. Each bit operates at sort of some different layer of abstraction. Like you don't have, for example, an organelle that gets, a large molecule that gets a bonus and just becomes like an organelle. So it's not a hierarchy. Some people call it like a holarchy. You could also think of how we construct ourselves as humans. We have like the individuals, then we have the family, then we have the village, the suburb, the city. So we're basically just composing our like human organizational structures. We don't go from individual world. But yeah, a lot of our distributed systems do that, sort of that one layer network. But natural systems have so many layers that trickle up. So then just some examples of natural networks. We have like the slime mold. So in this case, we're putting slime mold on a cutout of Japan, where Tokyo is. We're putting some like food and where all the major cities are. And then the slime mold is just kind of going to do a breadth-first search with the actual cellular material. And then it's going to, once it's found where the cities are, it's basically kind of prune the network. It's going to figure out where the things actually need to travel, and then prune the network. And sorry, these are all just unicellular organisms. Like there's no top-down control, there's no brain to them. Next example is like harvester ants. They forage for food using basically TCP. They connect with just like, their communication is like touching each other, so they'll just kind of like touch antennas. And TCP is how, on the internet we do congestion control. You basically send out a bunch of packets. You see if you get them back, it means that you probably have available bandwidth, and then you start sending more. And so the way the ants do this is, in the morning they'll send out some ants. Then they won't come back until they get food. Then the other ants kind of chill behind and are like, okay, waiting for those ants to come back. When those ants come back, they'll basically touch heads with the other ants, and they'll touch heads more when they get more food and less when they get less food. And then based on how much they touch those ants, then more ants will come out. So it is their way of doing congestion control, because if there is food, they'll go get the food, then they'll come back and they'll be like, touch everyone, and then everyone's like, sweet, let's just keep going, let's keep this rolling. If there isn't food, they'll go out, they won't come back, and then everyone's just like waiting, not trying to go out, because there's, you want to see where those first packets went. The example is the human brain. Human brain is composed of fractals. Possibly, this is kind of a little more, less sane science. But we are composed of neurons. Neurons are composed of likely into collections, probably storing information, topological features. As I mentioned before, brain's probabilistic, it's not deterministic. And they do fire on that one-to-many principle, where there'll be a threshold for whether some neuron will get fired. And so you could really think it, and then it will fire, or you could like not think it won't fire, and just barely think it will also fire. So now going to local distributed networks, just a possible approach to distributed digital systems. So why local? In nature, local distributed rules give rise to robust global systems. So as I mentioned, there's that fractal part. At each layer we have rules, and we just sort of compose those rules together, and we get new systems. And we see it in nature. We see it with, this was Great Barrier Reef, and we see like, it's come up in news recently, like as those systems are trying to protect themselves from the changes that are happening, like oceans getting more acidified, temperatures changing, and so we have like these bleaching effects, and it's really, there's no saying like, there's no top-down hierarchy there, it's all just there's local distributed rules that are basically trying to coordinate. So systems feature, as I would describe them, is the networks that who you connect to local people, whether it's based on social or geographic proximity. You say things that are subjective. It's from your perspective. It's not trying to get consensus around the world. It's just how you feel. And then you signal through local gossip, where you basically relay information through your peers. So the locations, this is just me as an example. I live in Newtown, Wellington, New Zealand. I work we're trying to build this professional family called Root Systems. Within this community, which is kind of our legal entity that we use, called Dev Academy. And then we're within this network of companies called Inspiral. This is how we do it with sort of fractal professional systems. And then I have like my side systems, so like the meetup that I organize, or like open source things I do. And so just thinking about pretty much everyone is part of multiple agents. So it's not you, the world, it's you and lots of layers, and just connecting with those layers. Subjective views, like I call myself Dinosaur online, my friends call me Mikey, my parents call me Michael. It's not that one is more valid than the other. We don't need to reach consensus, so what people can call me whatever they want. I don't really care. And we should sort of think of our systems like this. Gossip protocols relay messages through who's local to you. So for example, I can run into Alice in town and say, hey, like, what's the latest you've heard from Bob? And this is part of it's easy to do this with blockchain structures. So you sort of have these set messages that you're just gossiping the new messages to add to people's blockchains. So example, a little over time. So we've already seen SSP. SSP is the database that Patchwork's built on. It's a peer-to-peer log store. Each user has a feed associated with public and private key pair. Each feed is just a linked list of messages, each signed by the associated private key. Messages reference each other, and so you can use that to create links and indexes. So that's like when you mention someone, when you reply to your post, those are creating links that are in your message. Each user gossips with who they follow and who those users follow. So you're doing friends and friends of friends to get basically up to 2 hops of replication. The idea is you don't need to replicate with the world. You just need to replicate enough to get your messages to you. The public messages is just straight up JSON. If people have looked in the Patchwork, you can view the data and it's just JSON. You can also view private messages. If you look at those, they're just a blob of encrypted text. And because these messages don't have a to or from header, they're just like blockchains, then you don't know who it's from. You know who it's from because it's who it's signed by, but you don't know who it's to. So basically, when someone receives that, they're just like, well, was it from me? I'm just going to decrypt it and find that out. So you don't have the same problems as email decryption, where you don't decrypt the headers and email doesn't work without headers. In this case, the headers are the blockchain stuff, and then that doesn't have any information that's really could find you out too much. So there's Patchwork. Patchwork is the proof of concept social network built on top of it. Each user could create about messages about them or anyone. So you could say, this is what I call myself, this is what my avatar looks like. You could also have or this is what I think their avatar should be. There's no idea of a global namespace. You can pick whatever name you want yourself to be on Patchwork. And then anyone could just rename you and be like, well, I call you this. And then you can mention them with the name they've renamed to. So we don't need a global namespace. And then you have these post messages, which is kind of Twitter/Facebook style. But it's only proof of concept, really. There could just be an ecosystem of apps built on the same protocols. And someone has written GitSSP, which is basically GitHub but decentralized. So it's GitHub built on top of the same database as Patchwork. They've already re-implemented all of Git, and then now have already re-implemented all of basically the features of GitHub, like browsing stuff, or posting an issue, or making a pull request, or merging a pull request, or things like that. So demos, yeah. People have already been using Patchwork, so I think I'll just assume that's a demo enough. And yeah. People could ask me questions, but probably just ask me in person, because I took up 30 minutes.
You got what?
I took up 30 minutes.
Okay.
People can ask me questions.
All right, that's cool. Like it is kind of afternoon tea time.